So the next stop for us is the Archimedean property. So the Archimedean property is something that we already discussed many times. But now that we have the least upper bound property, we can actually prove it. And this is going to be important for us because we want to somehow be able to say that when we added all these new numbers to Q, uh, Q still dense in this new larger set. That means that between any two real numbers, we can find a rational number in between. So even though we may be adding actually a lot more numbers than we already had, I know the Q is a countable set. We know, we know that we're gonna talk about it kind of soon. But even though Q is set that contains infinitely many elements, the numbers that are in R that are not in Q, namely the rational numbers, they are a different kind of infinity. They have a different cardinal, what's called, and a different cardinality, and so that's yeah. So point is that even though we're adding these many numbers and many more than what we already had at the beginning, um, it's not so. The quantity or the ordered field that we have is not so overwhelmingly large that there are big gaps between numbers or the numbers in Q become very sparse sitting inside of the real numbers. Okay, so that's the discussion now. So it's all about the density of Q in R in the set of real numbers. We know that Q is an extension of n because we want to be able to divide the whole numbers into yet smaller ones. We want to have inverses for numbers when we add. We're considering the operation of adding two numbers, so plus. So we extend with this algebraic extension is so as to make n suitable. This extension of n make it suitable for adding and multiplying things and all that. Now we saw that we extended Q to create a new set which is called R, which contains all of its upper bounds, all of the upper bounds for bounded sets in this new set R. And the purpose of these properties is to indicate how this new, how R contains Q and N. How these two set of numbers sit inside of the set R. So the theorem, this is the theorem 1.4.2, which is just finally the Archimedean property. So we'll start with the first statement. So given any number x in R, there exists an and in n that is bigger than that given number. So satisfying that n is greater than x. Now, given any real number y greater than 0, there exists an n, and in n satisfying satisfying 1 over n is smaller than y. Okay, so let's stop for a minute. I mean, to talk about these two things. I mean, you may recall I from the last work session that we had, and in fact, this was derived as a consequence of a more general version of the Archimedean property. So in fact, they're equivalent to each other, as we'll see. But yeah. So the point here is that for that particular version, we said that n epsilon was greater than 1 for some n given an epsilon. So 1 over epsilon is basically x here. So even though it may look like a more general thing, because you're multiplying n by something, well, in fact, it is not. It is not more general. It's just the same statement written in a different way. The second statement is that statement. If you think of y as being epsilon, given any y greater than 0, n times epsilon is going to be greater than 1 for some n. And yeah, so in fact, as you said, we'll see it will become apparent from the proof that all we need is the property that we have a supremum for every bounded set sitting in R. So every subset of R that is bounded from above will have a supremum or a least upper bound. And the proof will be done by means of contradiction with the fact that we have that the set should have a supremum and therefore a least upper bound. And this is a very delicate point. So we could read perhaps part I as saying that n, the set of natural numbers, is not bounded above, because no matter what real number you pick, there's always an element in n that is bigger than that. But the thing is, in fact, you can the Dedekind cuts, which is a construction of real numbers that we carried out a few weeks ago, it's an ordered field that extends Q and that satisfies the least upper bound property. There are other constructions that for a number system, so ordered fields that contain Q such that n is bounded inside. I mean, this may sound like a strange idea, but it's just that we're talking about a very big kind of cardinal here for this set, for the new set. still an ordered field, and it still contains Q, but Q is so small inside it that in fact N is a bounded set in this new ordered field. But then, I mean, if you may have guessed, I mean, that the field defined this way, I mean, if the field for which N is bounded is not of much use to us. So we don't do calculus or anything like that, or analysis with it. Okay, I mean, there's some people that do, but for all the math that you've been doing, we've been dealing basically with the real numbers provided by the Dedekind cuts and this kind of extension of Q. So and so for this particular construction, we have the least upper bound property, so the existence of a supremum for any bounded set from above, and therefore we have the Archimedean properties we'll see. So here's the proof. So let's assume then that no, this is not true. So remember the statement we want to prove is for all x in R, there exists an n in N such that N is bigger than x. So that's the proposition that we are trying to show. Okay, so that's the that's our P. That's what we want to show is true. So we assume not. So we assume the negation of that. So there is an x in R such that for all n in N, N is less than or equal to x. So this is P, this is not P. Okay? So you assume not P holds. Okay? So suppose that not P is true. So there's an x in R, so there's an element in R that is bigger than any natural number. But this statement here means that this is saying so this statement says that N is bounded, and that we don't need that they're actually giving you're actually given an upper bound, and that x and is bounded, and I'll say so the x is bounded. I mean, you're just gonna, I don't want to confuse you, but this is actually telling you that x here is an upper bound for the natural numbers. There is an x, so x now is just one. It's one fixed number that you know there exists. You know there is one number x in R, such that no matter what n you pick, n is going to be below x, so it's going to be smaller than or equal to x. So this statement, as we said, says that n is bounded. What do we know about, well, first of all, let's notice that n is a subset of R. So if n is a subset of Q, a subset of R, and it's a bounded set, so that means it's bounded, well, it's bounded above. So therefore it has a least upper bound or a supremum. Remember the set R satisfies the least upper bound property. So it has the least upper bound. So let's call this upper bound alpha, as in the book. Called alpha. Now, if you remember one of the characterizations of one of the characterizations of the supremum said if we picked an epsilon and we subtracted epsilon from alpha, then we must find an element in n that is above that number. Here, here we choose epsilon equal 1, so that's a natural number. And then we're going to be able to find a natural number that is bigger than that. So we know that there is some n in n such that n is less than alpha minus 1. No, I'm sorry, that n is bigger than alpha minus 1. Alpha minus 1 is smaller than n. Remember that we had that if we subtract epsilon from the supremum, we must be able to find elements that are bigger than that. If for any epsilon, in particular for epsilon equals 1. So we know that there is an n such that alpha minus 1 is less than n. Okay, so that's a given. But then alpha is less than n plus 1, and that's why we chose epsilon to be equal to 1, so that we would be getting, once we move 1 to the other side, we would be getting a natural number. So this belongs to n. And now you see the problem here is that then alpha is smaller than one element in n, and in fact it's smaller than infinitely many of them. It's smaller than n plus 2 and smaller than n plus 3. And so it cannot be that alpha is smaller than n plus 1, which is in n, and this implies then that this implies that alpha is not an upper bound. It's not even an upper bound, so it cannot be a least upper bound. So this actually shows that the set n doesn't have a least upper bound. So that's a contradiction, right? This is a contradiction. This is certainly a contradiction, because if n were bounded, and since we are in R, then if n is bounded, then it should have a least upper bound. This is a contradiction. So, and what was the wrong thing? We assume here that there is an n and an x in R such that every n is bounded by x. So there's no such. So no such x exists. no such x exists. Okay, so that's actually the proof of the fact that given any x in R, there is a natural number that is bigger than that. Now to to prove the statement, the second statement, proof to I, we rewrite the property to I. So this is the proof of I. We simply rewrite it in a way that is it becomes a matter of finding a natural number bigger than a certain real number. Divide. Let us note. So let's note that one over n being less than y is equivalent to 1 over y being less than n. Okay, so once we notice that, we can say, okay, well, what is that this second property says? Saying that given any real number y, there exists an n in n such that 1 over n is less than y. What is the first property? The first property is that for every x in R, there exists an n in n such that n is bigger than that. So we already have, from the first statement, the fact that we can guarantee the existence of an n in n such that n is bigger than a certain number, any given number. And to prove 2i, then we just need to notice that if since I is true, the first part is true, we can set x to equal 1 over y. Right, actually, well, remember that y is greater than 0, so 1 over y is well defined, it's not equal to 0. Well, 1 over y is not defined because y is not equal to 0. So this is a well-defined number. So if we set x equals to 1 over y, we know already from I that there exists some n in n that is bigger than that x. There exists some n such that n is bigger than that x and happens to be equal to 1 over y, which is what we want to prove. So given y, remember what's given and what you need to find. We are given y and we're asked to find an n. And this is exactly what we've done. Now, with these two things in place, we are ready to prove the density of Q and R, which is a major thing. Okay, so this is this is what we're going to be doing next. Okay, so we'll see in the next video. So the point is here that remember that we can find an n such that 1 over n is smaller than any given number, no matter, any positive number. So no matter how small that number y may be, you can find an n so big so that 1 over n is going to be smaller than y. It's going to be greater than 0, of course, but smaller than y. And that's gonna allow us to find rational numbers inside any given interval. Because if you think of it this way, if you're taking steps that are a very small size, you're eventually going to land in every single interval, no matter how small they are. And this is the starting point of the proof of the next theorem, which is the theorem about the density of Q in R.